Our end note for the conference comes from Michael Houston, Chief Architect at NVIDIA. He's going to be talking about Selene and Supercollaboration.
Thank you. I'm doing pretty good. Let me get screen share working here. Can you guys hear me okay?
Can hear you just fine.
Okay, and then Zoom always covers the display button. All right, so I'm going to sort of shift gears, quite a bit from the previous talks, although I do overlap with Aaron a little bit. We're big container fans as well, but I'm going to talk about what it really takes to kind of build big machines, especially AI machines. I'm going to focus on some of the things that we generally don't talk about but are critical into doing this. So, simple way to say is if you want to go fast, you go alone, but if you want to go far, you go together. And the goal of, us building super pods and things like that is to enable a lot of people to fundamentally do, big iron AI type workloads. So we need a lot of people, within NVIDIA and then lots of partners to be able to come together to do big builds like this. The sheer amount of technology that we need to cover makes it that we have to collaborate, across so many different areas to succeed at what we do. So we have a lot of experience building these things. We've learned a lot along the way, and we've made lots of changes along the way. So, we started with DGX1s, and even at a data center level, interconnect level, we made certain decisions that we thought were right at the time as we were learning all this stuff. And, we learned about a lot of changes we wanted to make into how we build data centers, how we lay out data centers, how fabrics are laid out. And I'll talk, more about each of these. But, these are kind of more traditional flooded rooms, colos and things like that. And we figured out ways to kind of do things better. We've had other people build, and we've kind of moved around things, but each step along the way, each build we learned, more and more. And same thing as we got to DGX2s. This is a picture of Circe. So we went to very high density racks and kind of pushed a little too far. This was more towards the HPC side of things. Still, going in colos, but this was 44 kilowatts in a rack. Very dense InfiniBand. And one of the big things we learned here that's colored a lot of how we think about design is that we had to expand this multiple times. And it was very difficult for a fabric design. So we constantly had to kind of rebuild and repull cables and redesign the fabric. And so one of the key tenets in our newer builds to have much more modular designs through that. And what that means now and how you build data centers, how DC Ops deploys, how you do your fabric builds, we span so many teams to be able to do these things. So Selene is what's currently standing. So I won't torch you guys with all the stats, but it's it was a top 5 supercomputer. Now it's top 6 supercomputer. It's very balanced. It was designed to do AI, but it turns out that a big iron AI machine is also quite an excellent HPC machine in practice. We actually carry more interconnect and more storage performance than many of the systems around us in the top 500. And unsurprisingly, I/O performance is critical to doing machine learning, as you heard in the previous talks. And then what I'm in the middle of building right now is the next generation machine, which is EOS. So this is the rendering that was showed in the GTC keynote. And again, all the learnings that we've had on how to build these machines, especially in interconnect and storage requirements, all feed into this. So we learned so many lessons along the way building all of this, from logistics to literally how things are packaged, so much about cabling, how to think about speed and feed matching, thermal design, data center design, interconnects, how you deploy these things, how you operate these things, like telemetry, how you design for flexibility, because we have to walk into, or the point of superpods is to be able to walk into any data center on the planet and be able to deploy. Makes it kind of hard. So, how do we think about that? And then, ourselves as well as our customers, you have very hungry researchers and data science folks that want things online as fast as possible. So inevitably it means is you have to plan up front to expand. It also means you tend to be operating while building at the same time, which is good fun. So let me start with something that it's more of a fun anecdote, but it sort of shows you that you have to think all the way through, collaborating with things that you don't always think of. So when you build big machines, especially at the speed at which we build machines, things like logistics and packaging become a really big deal. So Selene was the first time where we actually had our data center operations folks actually help in design of the packaging. So these things, come on sort of these pallets. They're heavy machines, but we had to go through multiple iterations of, different server lifts and different forks and how you get into things, and protection from liquid, because these things are on airplanes, and if you go through Okinawa in the spring, it gets rained on. So these are all things you don't expect, but you have to design packaging for. So, but we had to design, how the boxes go together, how they can even be operated and taken apart in a data center to go fast, to how it comes apart. But what's interesting, and my favorite thing, was the first time they got boxes, we realized that it was very difficult to get a server lift in them, that they basically had to tear apart the box. So we actually sat there and redesigned the entire packaging solution for how server lifts work for people to go fast. You don't want people bending over and lifting these things up, so you need to use server lifts. So one of the innovations that was sort of come up with, Steve's obvious after the fact, is to actually have a box that was designed so the side panel would actually tear down. The initial boxes, they were cutting them out with box cutters, and then to actually have the packing material around it actually come out as well, so that you can nicely get a server lift in it. So, but these are just things that often we don't think about. And so this is literally collaboration all the way down from the people designing the servers to, through data center ops, to the people designing the cardboard boxes, and then actually our shippers. So, an interesting example of collaboration that sometimes, we don't think about. And then cables. So a lot of you, I'm sure, have set up machines or watched people set up machines and the amount of cables. So you talk about a machine like Selene, you're in hundreds of kilometers of fiber and tens of thousands of endpoints and transceivers. So cabling becomes a really big deal. And so you've probably seen sort of the bad cabling. And, this was some of our early cabling, like in our labs, to figure out how to do this, right? And you end up with nests of cables. If something needs to be debugged, you're like chasing this back. You have people that kink the cables. So if you look at the picture on the left, some, those bend radiuses aren't great, right? So how do you do better at this? And so you can see kind of the evolution of, a lab to, okay, let's do better, in the middle, and then, let's get pretty good and bundle things. But what we found doing Selene, and this is how we do all of our large builds now, it's kind of obvious after the fact, is once you build a rack elevation, you can measure all the cables. You know all the endpoints, so you can generate the labels, and most importantly, you can now generate the bundles ahead of time, which allows you to get so much more fiber in so much faster. A lot of data centers, they're still basically building the cables, completely on site and testing them and, and running them. And it's amazing how much faster you can go, right? So in days, we can get all the fiber, pulled and ready to go at these very high densities, that we run. You can see the densities into the quantum switches, the InfiniBand switches there on the right. So you get, nice, pretty dressing, which also helps. It helps a lot for debug. And then working with our networking team, we actually came up with a different labeling strategy. So the way that we lay out fabrics for SuperPods are very prescriptive. So we're what's called rail optimal or rail aligned. I'll show a picture a little bit later, but each of our machines on kind of the GPU compute fabric that we call it, we have 8 HCAs. So instead of going to a traditional TOR, we actually have HCA 0 on every machine go to leaf switch 0, then HCA 1 to leaf switch 1. So it's important which way things get cabled. When you deal with this many cables, it's a big deal. So being able to have, labeling, again, not something that you normally think of, but it's really important. It fundamentally changed how we deliver and deploy machines. And it also aligns when you do your fabric topology checks. So IB Diagnet, for those that use InfiniBand, it's now easy to validate because we have a full rack plan with all imports, and now you can validate it against the topology generated with the tools. And then, nice, pretty sort of cable porn, pictures here of what we do. But this is what all the deployments now look like because we have these bundled, nice standards as we go through things. Another interesting one is power cables. So yes, we have lots of colors. So sometimes people will say that the backs of our racks look like unicorn vomit. And EOS has even more colors because of the different types of cables and networking we have. But again, it makes it useful for data center operations. So we color code things. And the reason they're color coded here is those are aligned to both the phases delivered in the data center as well as the 2N redundancy in our case. So we spend a lot of time on cables. One of the things that we found in earlier builds is that getting the power cables always positively plugged in and not having them, come loose as other things are being maintained was a fairly big deal. So we actually moved to locking cables and then actually had some special cables designed. So we worked with a cable supplier to actually get these built. Again, another kind of surprising collaboration, but to make our lives significantly easier in the market. Then the obvious place for collaboration is all the chips and systems. So we have people that work on A100, a huge army of people, and deliver all these amazing technologies that go behind it. We work with the memory vendors to get HBM2E. We're often very, very early and sometimes the first to have a new memory technology up. We have research folks both inside and outside NVIDIA that work on very high-speed interconnects like NVLink. So we pull those in. So there's a tremendous amount of research and work that goes in here. And then working with our researchers and staring at how their codes work at a single chip level, then we look at things like tensor cores. So how do the algorithms really work and how do we build an optimized unit in the chip? One of the other advantages is because NVIDIA ourselves are a massive consumer and developer of AI, we get the advantage of knowing where our researchers are going as we decide to build new chips. So this is A100. We announced Hopper H100 a few weeks ago. All those things, we're watching what everybody's doing. So deep collaboration, and it's sort of a cliche word now, but fundamentally we're co-design all the way through. We know where our researchers are going. We know what they need, both internal researchers and external researchers, and we build technologies around that. Okay, so all these amazing technologies that are in the chip. Brand new numerical storage formats. Again, it's working with our internal and external collaborators. So this is TensorFloat 32. It's kind of a hybrid between FP32 and FP16. So the exponent of FP32 and the mantissa of FP16. And that can enable huge speed ups, once we do all the rest of the end-to-end work and integration work into all the DL frameworks. Again, another huge place of collaboration is we are very, very deep with every DL framework developer and almost every HPC application on the planet as well, actively doing coding and making sure that all the new technologies can be made use. And then we wrap that all into a system. So in the case of DGX A100, it runs AMD ROMs, and we did a lot of work with AMD around getting the I/O system, fully tuned to get the best performance through their CPUs. So also a tremendous amount of collaboration with AMD on how to really drive I/O. We are fundamentally an I/O monster. A tremendous amount of PCIe, a tremendous amount of interconnect, a lot of NVMe. It's sort of as much as we can possibly fit in a box is kind of what we do. So again, a lot of collaboration internally and externally to kind of make it happen. And then all the choices behind this is being done from our researchers' code and their directions, as well as deep simulation and performance analysis toolkits that we have internally that helps us make these trade-offs as we build these machines, because you can never quite get everything that you want, right? If I could, I would put 1,000 GPUs in a box. It's just not that practical. As I mentioned, a lot about I/O. So, I mentioned our work with AMD, but we also had a tremendous amount of work with our interconnect team, PCIe switch vendors, NVMe vendors, everything to get this tuned all the way up. The amount of firmware issues, for example, in NVMEs that we went through to get the correct tuning that we needed, Linux kernel patches to get certain performance things that we need, various kernel options, a lot of work with Canonical and Red Hat on OS level work in tuning, container toolkits. It's this huge thing that's all put together so that everything can run at maximum performance on these systems. Then once you have one box, why not put a lot of them together? So then we work on how do you design a scalable unit? And this is a logical thing for us. So in DGX A100, it was 20 machines, because that aligns with the radix of the switch. Why do we care about the radix of the switch? Because we want the maximum fabric performance. So deep interaction with the networking team to make that work. And then all that's done within communication libraries. So Nickel being one of those libraries to make sure this is all tuned out, right? So you can see the stack just kind of getting deeper and deeper and deeper. And the amount of people that have to build these things gets wider and wider. Thousands of people are involved getting everything built up and ready for these machines to go. So then all the way down to back to chassis design. How do you get the I/O out? How do you get the least amount of interference on cables when you rack these things all together? What is the right mix of things? Like philosophically, we separate compute and storage. Part of that is so that what we call a compute fabric, the ones closest to GPUs, can run InfiniBand, and the storage fabric can run Ethernet or InfiniBand. And then you need Ethernet for your in-band management and user access. But how do you lay all this out? And then how do you make it operable? So these are all separable trays so that it's easy to get things in and out and do replacements. And then same thing with the power supplies. We're designed to run full 2N so that we get the up times that we need to really be successful. So power is also a big one here. I don't have a deep slide on it, but you can see how much we put in a box. The amount of power we run is a big deal. And so we pushed the entire ecosystem and had a lot of voltage regulator vendors come with us to do 54 volt distribution inside the box, and then PSU vendors that could deal with the load and density of this, and then PDU vendors to then build the PDUs that could do it, and then all the way out through the data center, whether or not your Starlines or RPPs, to do it and manage power as we do this. So as I said, one of the tricks was to figure out how to be able to build this incrementally and expand out. So we do this with a notion of a scalable unit. As I said, 20 machines in the Ampere generation was our scalable unit. And we figure out how the ratios of things work so you can stamp out scalable units at a time and then build them into a fat tree. So there is some overhead here. You have to buy some extra switches if you want the expansion, but it makes it very, very, very fast to expand. And you can say operational while you expand, which is also turns out to be very important for us and most of our friends. And then I won't go into detail on all of this, but we plan out and figure out how to build big machines. And so we do it for ourselves. We do it with a lot of CSPs because it's not just DGX. We actually have white papers. We tell everybody how we build, how we route everything, why we do it so that it can be replicated, so that all of our software that we spend so much time optimizing and tuning will work on anything based off of the reference architectures. But fabric design is a big one. And we have a very specific one that we use in SuperPods. And as we get to really massive machines that some other people build, then we work with them on modifications that they need because of space or distance limits in their data centers. Some data centers that are big, they're really long and narrow, and so you have to very carefully think through what your cable distances are, right? You don't want a whole bunch of kilometer-long cables, right? Ideally, everything is in 30 or 50 meters, but we have to sort of play that out. Or we have some people that want machines that have to span floors in a data center or sometimes even buildings. And so that also makes changes. But we have a base design and we understand where we can bend that design without having to do a whole bunch of extra software work, which then delays time to solution. So what's often deployed at this point in time is about 1,000 GPU Ampere type things. So 128, but remember that sort of modulus of 20. So 140 DGXs is a pretty common build. And usually people start off with like 2 scalable units and then build up, and then they cross over and get to bigger things. So Selene being a 4K, 4,000 GPU supercomputer, 560 machines technically. The other big thing that we spend a lot of time on and work with a lot of people internally as well as a lot of storage vendors is to get the storage hierarchy built. Right, was Aaron sort of mentioned in the last talk, it's storage is kind of a big deal, right? AI is data driven. So we spend a lot of time in our architectures and then on our software on how to build a storage hierarchy. So view it as extending a cache. So you have your memory cache. So in the case of Selene, 224 terabytes per second, aggregate in about 1.1 petabytes of aggregate memory. And then we have a lot of NVMe in the node, as I mentioned as quickly as I was showing those block diagrams. And we function that either as a pull-through cache. So like with Lustre, you have persistent client caching. GPFS has ROC. And so you can do it that way. We have interactions with our scheduler. So when the job starts or before the job starts, you can pre-stage data with data movers, things like that. So if you notice, it's significantly larger in size, but significantly slower. Then we have parallel file systems. So Lustre's what's deployed in Selene, but we work with many other storage vendors, but you need something pretty fast. So Selene theoretical is about 2 terabytes per second to about 10 petabyte of usable. Right, it's bigger than that, but with how we have Lustre set up, about 10 petabyte usable. And then we go off to object store. So big spinning disks. So we have hundreds of petabytes of data that we get to 100 gigabytes per second. So again, there's a lot of interaction with a lot of different vendors and a lot of software to stitch all this together. And it's sort of part of what we do with the SuperPod, but we're fundamentally trying to pull the ecosystem and collaborate with people to do things. One quick note that I'll have, it's one of these other fun collaboration things, is especially if you operate these machines or if you're a developer, you'll notice that people always want the easy way and they want to use tons and tons and tons of small files, right? 100 million 1K files. You will crush any storage system on the planet. So a lot of what we've been working on and collaborating with others on is to get people to be using more polite file containers. So things like record IO, TF record, web data loader, indexable tar files, because it is so much more polite on the file systems to do this. So it's another kind of interesting example there. And then we develop brand new technologies. So with our friends in the networking unit, right, we have Sharp. So one of the key things in machine learning is an all reduce. And the next generation, which is Sharp 3, has even more capabilities. But again, one of the things we began to notice is we're spending a lot of sort of compute time actually doing the reduction work. So, calculating the average of a tensor across multiple workers. So wouldn't it be nice to push that into the fabric? And so that's what Sharp is. And Sharp, gives very nice gains in the sweet spot of all reduces for, deep learning. And the next generation, right, we did more analysis based on what we were seeing here to then tune that and then expand the types of collectives that we can offload and do. Again, to get more efficiency as well as much better overlap and lower latency if you can't overlap compute and computation, which we see in some forms of model parallelism. So if you're tensor parallel, there's really nowhere to hide. You have to communicate the data. So you want to be as low latency and as fast as possible. And then all this is integrated into Nickel, which is then integrated into every framework on the planet. So normally if you're doing distributed training as a user, you don't have to really think about anything because all the software down to all the hardware has been done and been optimized. So still moving along kind of fast. So we also now get involved with a lot of data center design. So there's, kind of a quick and dirty sketch of the data center that Selene is sitting in and how it's laid out. So you think back to the original pictures that I showed, all the early systems were flooded room, kind of hyperscale traditional colo design. And we realized we can do much better on thermals and be much more power efficient if we switch to different types of containment. So Selene is a cold IO containment solution. I'll talk a little bit more about that. I have an airflow diagram that I'll show you in a bit. So one of the things now we also do and collaborate with a lot of people on, and CFD has been GPU accelerated for a long time, but we do CFD models ourselves, and then for our partners and for all customers that do SuperPod deployments so we can figure out the best way to lay things out. And I won't go into detail of all the pictures, but it can be amazing how much just little changes given, whether or not you're hot aisle or cold aisle or flooded room, little changes in racking position can make. And then especially in some situations, how the heat will actually loop over the tops of the racks or around things and, and mess up, your whole thing. So we spend a lot of time on CFD for ourselves and for our partners and figuring out the best thing to do. So what we did for Selene is we went to cold aisle containment. So we were on a raised floor, so this is fairly easy. So what we found is the neat thing about cold aisle containment is we can be positive pressure. And one of the issues that we were seeing in a lot of our internal installs, as well as some customer installs, is we would see an inlet temperature difference between the top and the bottom of a rack by a few degrees centigrade. When you're in cold aisle containment and positive pressure, there's less than half a degree difference between the top and the bottom node. And with modern processors wanting to operate at boost clocks, the colder that you keep them, the higher the boost clock that you get and the better performance you get. It also means you get less jitter because it's now easier for everybody to run at the same clock depending on the bin quality of their chip. So we get much better overall stable performance across things. The other thing is you're as directly cooling the machines with air as you possibly can in this setup, right? You're not cooling the rest of the room. The hot air comes out of containment and goes up back to be recirculated, back in. So I'm not spending time, cooling a room. So it does mean it is quite cold if you walk inside of one of these pods, and it is a little toasty when you're outside of the pod. As I said, though, we do a lot of work with people on hot aisle containment, which works as well, and we do the CFD and kind of work through that. But we do have to fundamentally think about these things to get to power efficiency. As part of that, it also means we do liquid prototypes. So we do a lot of work on designing, liquid cold plates, manifolds, CDUs, secondaries, primaries, interactions with data center vendors to try to figure out, the better way to get efficiency. So in a data center, kind of like I just showed you, if we convert to liquid and we get to turn off, basically almost all the fans in the nodes, we get about 15% efficiency improvement. Now, part of that's from the fans, and then part of that is because the chips are staying cooler, you can end up with a more optimal place on the voltage frequency curve. You have less, your junction temperatures aren't as high, and so you can begin pushing some things around. So, liquid is still not super easy, to deploy, but these are the things that we're working with the entire industry and ecosystem on in order to make this much more deployable, not some weird custom thing, but something where it's very clear what to do and what the flow rates, pressures, temperatures, fluid types are that that can make this work. So we're doing this with our with a bunch of the traditional liquid vendors as well as the data center vendors and several of the hyperscalers. We're all working on these types of things together. And if you fully designed a data center for scratch for liquid, you can probably get closer to 20-25% better energy efficiency than a traditional air-based data center. And then we also explore other advanced things like immersion, cooling, and things like that. But liquid is one of those things where it looks like that's something that can be done here, pretty quick, and it's not that strange. And a lot of data centers can be converted either doing facility liquid or doing liquid to air. So doing heat exchangers, either on the floor, back into the air system they have, or heat exchangers up to the roof and out. So Aaron actually talked about containers. So as I said, we're also huge fans of containers. And one of the reasons for that is from an admin perspective, it sure makes your life easy when somebody's not asking you to install a certain version of Python or SVN or Git or whatever, and you have the thinnest possible node. It also means it's much easier now to do things like stateless boot because you need something really, really small because basically everything should be in containers. So then containers, we view it as less of a kind of fake VM and more of a way that all of the application, all of its dependencies are integrated into one place. What's nice about this is the same containers that we build and that we publish, they run on SuperPods, they'll run on your Linux workstation, they'll run on AWS, GCP, Azure, Baidu, Alibaba. It's the same thing that runs everywhere, which is kind of neat. So you're not fighting or debating, right? Because everything the application needs, all its dependencies are integrated into the container, which is pretty cool. And then we support containers on multi-node, and we spend a lot of time working here. So a lot of work with the Docker community, a lot of work with the Kubernetes community, and then we've also built some of our own very low-level, lightweight, fast container systems. So nroot and Pixis is what we use to do that. So what are stack in general looks like, it's fairly simple and thin and light, which is why it can be, rapidly deployed everywhere. So Selene today, and then our base command machines in the wild run Slurm, and then to get containers to work with Slurm, use a plugin called Pixis that then launches en route in our case, or it can launch Docker. We use en route because it's super thin, which allows us to get all of the advanced networking stuff through really trivially, and it's super lightweight. It doesn't require extended permissions to run it. And en route and modern Singularity have a whole lot in common. People that are Unix geeks, all en route really is chroot with C groups. So it's super lightweight, using the protection mechanisms in the Linux kernel itself. Then monitoring. So monitoring telemetry is another huge one. So hopefully this doesn't look weird to anybody because it's just Grafana, but we spend a lot of time pulling different types of telemetry, and we work heavily with Prometheus and InfluxDB as two examples of the backends that we use for different data types. But this is where we push ourselves and we push everybody to get us reliable telemetry. So every Ethernet switch that we deploy, all of our PDUs are smart PDUs and are monitorable. And a lot of this, it makes it so much nicer for admins. But as it turns out, if you have the correct monitoring telemetry, it means debugging an application at scale. We can almost do it from Grafana, right? We can tell if somebody is CPU limited, they're IO limited, if they're not using the GPU very well, because we can watch PCIe rates, network rates, IO rates, page fault rates, and it's amazing how far you can get with monitoring. The other reason we do monitoring is one of my team's jobs is we go to scale during bring up. So as soon as the new silicon comes back, the new systems come back, we go to scale immediately. And so telemetry is bread and butter. But it's all open source tools that we use, and we're heavily active pushing code back and forth and working with folks. So these are just various examples of scatter plots that we use to begin trying to find anomalies in the clusters. And very quickly you start being able to look at graphs once you get used to it and you understand where something funky is happening. One really specific case is here's a monitoring example of Megatron, so a very large language model running. And remember what I said about debug. We can kind of quickly find some issues. So the first thing is this is a very highly tuned application. So on a box that has 6.5 kilowatts of theoretical power draw, this is pulling 5.4. It's the most expensive power application that we have. You see that it ramps up pretty quick as it starts. You can see the CPU bump as it's basically indexing and getting all the Python stuff working, and it kicks off and goes. And then you see the GPU kick up, which means the overall system power kicks up. And then you see a bit of a drop for a second, and then it's nice and stable, kind to the end. And this is a power view of the world. So you zoom in, you look at the GPU view. So we can zoom in, so it's the same telemetry system. You can zoom in. So you see that big first drop, then you see kind of a drop that looks like a heartbeat, right? In some ways this looks like a heart rate monitor. And then you see a big drop at the end. Well, that first drop, as it turns out, that's at the end of the first epoch, and this is effectively this is PyTorch. This is effectively when the graph and everything else starts to settle in JIT. It also means this is when they complete all their reindexing. So there's a performance tuning opportunity here. The other thing that happens on an epoch boundary is this is an artifact of how the optimizer state currently works in PyTorch. So every time you restart to a new epoch, there's a whole bunch of stuff that happens. There's actually not a checkpoint here. The checkpoint is the really funky drop about 3/4 of the way or 80% of the way through this. But again, you can kind of see these heartbeats on the outside. So, but it also shows that a highly tuned application is just pegging the GPU. The GPU is busy all the time. The SMs, which are kind of, the ALUs are busy all the time. The percentage of tensor ops, which is the big workhorse, is very high. This is one of the most highly tuned, applications. And there was a supercomputing paper last year that goes into a lot more detail about all the performance tuning and, specs like, how much bisection bandwidth they're using at a given time or storage bandwidth. But it's kind of an interesting thing that you can get out of staring at telemetry. So that was a super quick run through of all just the different types of collaboration and things that we tackle and look at. And that's kind of what I wanted to give you guys a view of. I've given lots of technical talks about, Selene, but I want to show some of the surprising ones. Like, people are often surprised by packaging, that we actually have to go all the way down to packaging. It's just that stuff really matters in practice, or cabling really, really matters in practice, or data center designs, right? We don't want to have to wait for a brand new building to be built that will house this machine like most supercomputers are built. We want this thing to be able to go everywhere, but we need to work with people, right? We want to get everybody in the world to 35 kilowatt racks. That would be great, but most people aren't, right? Most people are like at 15. So, what's the balance in what we do? All right, so that's it for me. If there's questions, I'd love to take them.
Thanks, Mike. Really great presentation on Selene. When you're looking at other systems like Cambridge One, and then you'd mentioned the upcoming EOS platform, any differences to the approach?
Yeah, so let's talk about Cambridge One. So Cambridge One is still the same logical layout, but if you look at the pictures of Cambridge One, it is 2 systems per rack. That was the available power density in that one, but it still lays out all the same. So still, instead of 5 racks being a scalable unit, it's now 10 racks being a scalable unit. And then that data center is on slab, and basically it's hot aisle containment is the effective behavior of that machine. It doesn't have the big plenums, so it's kind of halfway between flooded and hot aisle containment. But the same building blocks all work, and that's kind of the point of what we do. So all the cable bundling, calculating cable lengths, it's kind of a big machine that works, to deploy these things. University of Florida is higher density. They run 5 machines in a rack, right? So 4 racks for a scalable unit. They also use vertical PDUs instead of the horizontal PDUs like we do. But again, the same logical way that these things are built, they're all built the same. So when we log into these machines, they all look the same to a user. There's no difference. It's just the specifics of fitting into the data center. And again, that's why, there's some trade-offs we have to make. If I was able to do fully custom enclosed racks, yeah, there's some tuning things that I could do. But again, the goal is to be able to deploy these things rapidly and fast anywhere.
Great, thanks. I currently don't have any questions in the queue. So thank you again. Appreciate the end note.
Sure.
Thank you for joining us.
Thank you.